Welcome, everybody. So, the speaker today is Soumik from the University of Chicago. Many of you were probably at his previous talk on Monday. Anyway, I'll introduce you again. Soumik is a third-year graduate student at the University of Chicago. Before that, he did his master's at the University of Waterloo. And in 2018, he got his bachelor's from Jalandhar University. Welcome again.
Thank you so much. And thank you so much for having me here. Show me here. Today, I'm going to talk about pseudoentanglement. And this is joint work with our friends and collaborators from Stanford, Chicago, Texas. Let's begin. So this will be sufficiently broad, but feel free to pause me with doubts that you get. So what will we cover here? Let me give you a brief sneak peek of this. So first will be motivation of this new concept of pseudoentanglement. The second part of the talk will be some old constructions that we had, which was presented at QIP this year, and that was recorded. So those of you who have seen that recording, this part might just be a recap, but that's not the end of it. For this talk, especially, what we will talk about is some very new constructions that we very recently proved, like in the last few months. And this is entirely new. This hasn't been presented before. So then we will segue into this new construction. And finally, I will end with applications of pseudoentanglement. There's still a lot to discover there. We have barely started scratching the surface. I will get to that when I go there. And this is where I need your help in designing new things from pseudoentanglement. Let's begin. This property of high entanglement or just entanglement, that's a driving force of quantum computing. This phenomenon has been studied by many scientists for many decades. This was, for instance, the topic that won the Nobel Prize in Physics in 2020. But there's still a lot that's left to be discovered about this phenomenon. And what's a one-sentence summary of this talk? So in this talk, we will give you a new property for this phenomenon. So what is that property? Let me try to motivate that with a sufficiently high-level question. So this phenomenon that you saw, entanglement, let me ask this. Is this phenomenon feelable, quote unquote? Now, like, what do I mean by feelable? Entanglement being feelable means something like this concretely. Say there's an efficient quantum procedure. And what do I do to to that procedure? I give like one of two things. Say I have a collection of states with high entanglement. I draw a state from there, make polynomially many copies of it, and feed it to this procedure. Or I have a state collection with low entanglement. I take a state from there, make polynomially many copies, feed it to that procedure. Will this procedure be able to distinguish between these two collections, given polynomially many copies? And what we will show is that no, it cannot. There are state collections that we will construct where this procedure fails to distinguish between the high entanglement from the low entanglement. Any questions still here?
So what's the order of quantification? That is, for every procedure, there exists a pair of collections, or for there is a collection, so that no polynomial time procedure that you apply can distinguish.
The second one.
Second.
Yes. This is like a particular collection such that this happens. So generically, this phenomenon is not feelable.
So will you be defining entanglement in a feelable sort of way?
And so I will get to the concrete definitions here. The next few slides will make this thing much more concrete than what we have. More questions? Okay. So this unfeelability, this thing that we just discussed, I will talk about unfeelability in the context of random quantum states. The reason for doing that will become clear in the next slides. This is just a sandbox, for instance, just for now. So we will discuss this in this particular context. So let me motivate you random quantum states. What do I mean by it? These are states drawn from the Haar-random. Just have the valid collection of quantum states in some sense and just draw a state from that, like a hat. Why do we care? Well, these states have many potential applications. But there's a small caveat. You need to prepare these states in polynomial time to have harness these nice properties. And that's not possible. Generically, if you draw a random state, the circuit complexity to prepare that's like super polynomial, that blows. For a CS cloud, think of this as random functions. So Haar-random states, these random quantum states, they have limited practical applications because of this bottleneck. So what is the solution to this? Well, the solution is something very borrowed from CS theory in some sense. We will talk about pseudorandom quantum states. It's like some sort of a best of both worlds type. These are states that will mimic Haar-random states. And just like in CS theory, pseudorandomness will actually have two components. One is the statistical component, statistical pseudorandomness. And in the quantum world, we give a fancy name to this. This is called quantum T designs. What does this mean? So concretely.
So usually pseudorandomness is defined in terms of I. Whom it is pseudorandom in the eyes of the product here is with respect to quantum algorithms? Or
yes,
with respect to quantum algorithms.
Yeah,
okay.
That's correct.
You will come to a more formal definition.
I will come to the more formal definition very soon. I did say polynomial time. Yeah,
Statistical.
Yeah. So that's the subtlety that I will just come to. But statistical pseudorandomness, this T design thing, this is actually no matter what the runtime is since the guarantee is statistical. So T designs say that you have a collection of states, you take a state from there, make T copies. So this state, if you feed to a distinguisher, like a quantum distinguisher, no matter the runtime of the distinguisher, no one will be able to tell that apart from T copies of a Haar-random.
So is it T copy of the state or this? So I'm trying to compare with the T by the independence. So
yes.
They get T here, and their joint distribution is.
No, here the same state make T copies
and then
yeah.
So this indistinguishability here is up to some error?
Up to some error, yeah.
Some order one.
Some yeah, precisely. Okay, so why do we care about T designs? So these things have practical applications in many places, like benchmarking, quantums, these speed up demonstrations that we saw on Monday. Why? Because there are ways to prepare quantum T designs with polynomial sized quantum circuits. For instance, it's conjectured or proven even in some regimes that T designs can be prepared by geometrically local random quantum circuits with say poly. Questions here.
So you said that it's the same state with T copies, right?
Yeah.
So why does the T help at all then in this definition?
Yeah, the reason T helps, like the reason this definition gets stronger if you have this guarantee for T copies is because if you have more copies of a state, then the hope, and this is like borne out by math as well, the power that the distinguisher gets becomes more, because now the distinguisher can run very complicated measurements, like on joint measurements, like with respect to the whole, like the number of copies of the state that you have. And these joint measurements might help you in like telling apart these states from, like, let's say.
So you think of the B tens and B tens and B tens.
Exactly, yeah. For the same field that is like chosen at random in the beginning and then fixed.
So the difference of classification is in quantum, this is not a free operation.
We don't know how to prepare B tensor.
You can't arbitrarily copy.
You can't arbitrarily.
So this is the quantum analog of epsilon T-wise independence.
Ah.
Not right. Because that would require a joint distribution over T.
Okay.
So that's why I also got it, but it's not.
So yeah, this thing is just like you have a collection of states, you take a state like randomly from there, make T copies of this state,
and then compare it against T copies
of the same Haar-random, like yeah.
But isn't there also drawing one from
the Haar distribution, fixing then taking T copies.
If you take a random state from the T design, it's called like U, and a random state from the Haar, which is called V, and then you're comparing U tensor, U T tensor, and V tensor, same V. Okay, so that's why it's very different from T.
But I mean, if these are mixed states, then it amounts to having multiple samples.
Yeah, these are pure states.
Like you say T states, then so suppose it was a distribution, say classical, if you drawing K samples, so here are two distributions, you want to distinguish. It sort of seems reasonable that if you had multiple samples from both the copies, your chances of distinguishing them would be better. So you can, I mean, the power of T here is similar to it.
Then it comes to an exact analog of, does it come to?
No, because there it will be a joint distribution.
It will be a joint.
The T copies of the independent samples, I give you T times, and there was a random distribution, and from that I gave you T times. Will you be able to distinguish?
No, but these are not independent samples.
Sorry. Yeah. If the state itself is a mixed state, which means it is, I mean, some random variable. Right? When you say T states, that means each time you observe the state, you are going to get a different outcome, because the state is now a random object.
No, but I understand, but okay, I see. Because there's an independent probability, because each time you do a measurement, it's an independent probability.
From the same measurement, you might get a different result.
There's no conditional that's because I drew from there, I can't gain something from.
So there is no joint. There's no joint. Okay.
Or it's like when you pick IID, you say that it is the same random variable. Say I have x1, x2, x3, xn, and suppose they are drawn from the same distribution. I can say they are drawn from the same distribution, so they are the same random variable.
No, but if I make the same copy.
No, here the copying is at the random variable level. It is copying the distribution, not copying. When they say copy a state, it means the state has been copied.
Yeah, so just to recap like the setting, it's like, say I have a collection of states. Say I draw a state from there, like a particular fixed, like pure state from there, say I draw a pure state from there, then make T copies for that pure state, and then feed to the distribution.
So in that case, it is different. These are two pure states.
Yeah, these are T copies of two pure states, but the choice of each of these states, like the choice is random, like in the beginning.
Yeah, so in that case, I mean, what I said doesn't apply, because what I was.
Yeah, this is for mixed states. Yeah. So these are pure states. Yeah.
Then it's because so it's like you. So this the thing is CPN, right? The states are in CPN.
Yeah. So yeah, like a Hilbert space tensor, like T times.
So then, how does this tensoring help? Because it is mapping it into some bigger.
The reason tensoring helps is because, say there are two quantum states, like two pure states, that are like some trace distance part, let's say some trace distance part. Then there's a measurement, like there's a measurement that can be done on these states, like on multiple copies of this state, such that at some point these states these states can be distinguished.
One thing if you got that more, you just think of this as t, like you just whatever test you have, you do it t times. If it fails t times, then that your confidence is higher.
And the reason like this buys you something is because for quantum, if you have t copies of something, like t copies of a state, let's say, then you can make complicated joint measurements like on the t copies simultaneous. And this is much more subtle than, let's say, taking a copy and then measuring and like just doing it.
It's in the metric somehow.
Yeah, it's in the metric somehow. Like there could be very complicated joint measurements that you can do. And these joint measurements will give you more data than just like single copy. And that's why t copies.
Independence is still being maintained. There is independence. So suppose there was a state and you were performing a measurement. There were two different states and you were performing measurement. This was yielding a probability of p, and this was yielding a probability of p plus s. Okay. Now, if you had t copies of them, then you want to know whether you were again and again picking this vector or again and again picking this vector. And by you will be able to tell them apart much better if you had t copies. So even though these are pure states, your measurements will induce a distribution, and it is like you have IID samples. Yeah.
More questions? Do keep them coming.
We only ask for questions here, answers are also being offered. So
Yeah. Questions and answers. Yeah, of course.
Please go ahead. Yes.
Okay, so this is one form of pseudorandomness.
No, so as I told you, I mean, today's slot is actually a long slot.
Right, yeah.
So yeah, don't feel rushed because.
Sure.
But yeah, I mean, as I said,
Yeah.
people probably have other commitments, so try to.
Sure.
1 hour.
Yeah,
and
sounds good. Of course.
We can continue the.
Of course, yeah. So let's.
Corollary of this would be the fact that degree t polynomials, at most degree t polynomials of a fixed bounded measure can't distinguish these two. I have a
Polynomial on the amplitudes or something like that. Okay, see.
Yeah, this means some like statistical property of these states, like something can be said regarding.
Okay.
But for the next notion of pseudorandomness, the computational one, things get much more subtle. Okay, so this is borrowed from CS again, and this requires some conjecture to go through. Like there's some conjecture. Yeah, these are like conditional statements. So what do I mean by computationally pseudorandom quantum states? So these were defined by Liu and Song, like a couple of these were like defined by Liu and Song, like in a paper that got into print. So let's recap the definition. So a collection is called computationally pseudorandom, like a collection of pure states, if number one, given a key k, each state of this family has a polynomial size circuit description. However, this key k, which corresponds to each k corresponds to a state, like each key corresponds to a state for this collection. And if this key k is a secret, then there's no polynomial time quantum distinguisher that can distinguish between polynomially many copies of a state drawn from here from polynomially many copies of like Haar-random. That is, more concretely, for all polynomial time distinguishers A, the following statement holds true. So with high probability, like with respect to the choice of a state, the distinguishing bias is negligible. Like by negligible, I mean strictly less than strictly less than super polynomial less than.
So here there are two polynomials. One is the number of copies as well as the how much the quantum algorithm, the running time of the quantum algorithm.
Yeah, so the guarantee is that no matter how you choose these polynomials, states from this family line will satisfy.
Okay.
So note two subtleties or differences between these and statistical T designs. The first is, in some sense, the guarantee here is much stronger. How? So for T designs, the guarantee that these states could not be distinguished was with respect to a fixed T. Like the T could have been a polynomial, but that was a fixed polynomial. Here we have, like, no matter what polynomial you choose, this guarantee goes. So that's stronger. But what do we lose out? What we lose out is the runtime. Here the distinguisher is restricted to the polynomial type. That wasn't the case for T designs.
What is N here?
N is the number of qubits.
So it's
The state.
Sorry, this may be a stupid question, but what is the difference between K and M sub Q?
K and F sub, this is, yeah, there's no difference. The difference will be clear in some sense the next slide. This is just how we define the state. The state had like shy f of it is just like some bad notation, let's suppose.
So given a K, I can prepare a K state.
Yeah, basically. This is just like some like bad.
In a classical setup, the FA would be like, say, I'm encrypting with the symmetric, like some AES type thing. So key K and I encrypt it with some system like AES. And then I expect that the distribution I get on the output should be indistinguishable from uniform for any.
Right. So the reason I have the notation like this is just because the pseudorandom state family that like we will see, like just see, will be defined with respect to pseudorandom function. And that function is in some sense the F. But let's not talk about that now. Let's talk about that when we get there. It's just for now, it's just bad notation.
These are realizable.
Yeah, these are realizable. Yeah. By low depth quantum circuits.
Okay.
More questions here?
They're realizable under some assumption.
Yeah. And it's like the standard crypto concepts.
Yeah, similar to the even in the.
But
One is a
algorithm is not required to guess the key or anything.
No, it's just required to distinguish. Yes, it doesn't need to guess. Entanglement and pseudorandomness. These are the two concepts that we talked about. So how are they related? Here we will talk about how to concretely measure them. So it will be measured in terms of the von Neumann measure. Like we take a quantum state, we make a bipartition. For now, say a fixed bipartition. And then we just look at the von Neumann measure of the density matrices that you have on like each end. And that's how
even before measurement analysis has the definition.
The definition, this is the definition, like this is how we define high or low end.
But so that partition is it's entangled with respect to a fixed partition.
For now, let's say that's the case. We will see. Yeah. For now, let's say it's a fixed partition. We will modify that. We will come to that and get something much stronger.
And when in the previous slide, when you were talking about pseudorandomness, the observation, those rules are restricted to a particular subset, or like with respect to the cut.
There was no notion of a cut. Yes. In this case, for these constructions, the guarantee will still be like pretty generic, the guarantee of pseudorandomness. This cut business is just to measure if a state has high or low entanglement. So these are like sufficiently decoupled in some sense. Okay, so for Haar-random states, they have high entanglement. And same for T designs, like the statistical pseudorandom, like those collections that we saw. For T, like for Haar-random states, the fact that they have high entanglement, this just follows from like previous math papers from the 90s. Like Page's theorem, for instance. This was sufficiently recent, not that recent, but we know that both of these collections have high entanglement. But how,
Here we are still considering a fixed partition, right?
for these two cases, these will have high entanglement no matter like the cut. Yeah, provided that the cut is sufficiently large.
In balance.
Yeah. Okay, so how about like computationally, like how about this last row? Here, the picture gets much more subtle. We had a lower bound before, and the lower bound was strictly more than logarithm. If this meant, in some sense, that if a state had very low entanglement, like really low, like less than logarithmic, then there was a distinguishing that these people, the paper that talked about random states, these people found out that distinguished those from Haar-random states. And so the distinguisher started failing, like started being like super polynomial there, when the low entanglement was like just like that satisfied this strictly more than logarithm. But this leaves a question, right? Like, is this lower bound right?
So just to understand,
Yes.
if somebody gave state with low entanglement, no matter what state, they would be able to design an algorithm which will distinguish it from truly random.
Yeah, that's correct. Yeah.
But the algorithm will depend
On how much
on the particular
entanglement you go. Yeah.
Okay.
So it will depend only on the entanglement. Or
Just
it will
on
also
the
depend on the
entanglement.
set, on the particular.
No, not the set, not the set. Just the fact that it has very low entanglement.
Sorry, this is probably again a stupid question.
Sure, sure.
Suppose I look at the entanglement entropy of say 2 qubits in the state. That's always going to be very less than R.
Yeah, but same for Haar-random because so like that won't be a distinction.
Right. So when you say any cut, you mean
Like sufficiently large cuts, like cuts that grow with like say for Haar-random sets, so like maximal high entanglement just means for cuts that grow with the system size.
systems?
Yeah, because yeah, like I said, like there are trivial bounds.
Right.
More questions?
What you're doing is more than separating two probability measures that are close to each other, isn't it, from the samples.
I didn't fully get the question.
No, wait, suppose I give you two probabilities measures which are close to each other and I generate samples from both of them.
Yeah.
And I want to distinguish and say the samples are not coming from one, they're coming from the other.
Right.
That requires certain amount of tools and techniques.
Yeah.
So what you're going to be using is different from that, or is it going to be similar?
So it's going to be slightly different because so what we would be given here are not samples but quantum states itself. And what this paper shows is that if you have very low entanglement, then you can perform a joint measurement like with respect to some copies of the quantum state that you're given and can actually compute the fact that you have low entanglement. And so that's the distribution. Haar-random states have high entanglement. But if you have a low entanglement connection, then this distribution, this is called a swap test. This is like a very simple distribution. So, and this is something that I can talk about later, right? But yeah, so this distribution does a very simple joint measurement and computes the, and like calculates the like the low entanglement and distinguishes that from it. Yes, like the case study have like high. Any questions? Okay, so did this motivation make sense in some sense? So the goal is to see if this lower bound is stacked. And what do we prove? We prove that yes, the lower bound is stacked. We give the fast construction of optimally low entanglement pseudorandom quantum states. Furthermore, we give a very simple way of tuning the von Neumann measure of these states. So from all values between strictly larger than logn to L, we have a collection of pseudorandom quantum states such that the von Neumann measure will be that. Like a bespoke collection, depending on like how much like low, like a bespoke collection, depending on how much low or high entanglement you need.
So is it fair to say that like somebody asked, how much entanglement do you need in full efficient quantum computation?
Yes.
And your answer is not much.
Not much. Yeah, correct. Yes. Yeah, like I said, this gives a wide range of like like pseudorandom quantum states with different quantum features.
Sorry.
You will have to defend my statement. No, I mean, see, so I mean, there was this logn to the power c, right? Now they are able to construct states which have only logn to the power c entanglement and are still not distinguishable from random states. So
These are
for the behavior of
Under
random or an efficient computation's behavior on randomly generated states is no different from this. So one would have thought the inputs that you are pseudo-random inputs that you are providing look like random states. But one would have thought looking like a random state means high entanglement. But that is not true. I mean, it looks like efficient quantum computation can be fooled by states
Under crypto.
So how is this different from the IW generator, which takes log and random bits, push it to something, and classically polynomial algorithms are not able to distinguish? Is it the quantum version of that? This one that is there is if you are in if the beholder is a quantum algorithm under certain cryptographic assumptions, all that you need are just polylog and bits of entanglement. Is that what this is?
So I'm not sure of this concept that you mentioned. I don't know of this. I think one subtlety could, it probably might be thought of as like a version that's more quantum, and that's it, like the thing that you said. But I think the more like the subtlety here is that the input that we are given, these are not samples or bits, but these are actually states.
Yeah.
And since like we are given states and polynomially many copies of a state, the things that you can do, the range of things that you can do to these states, that blows up in some sense. There's a lot of complicated things that you can do.
Analog of de-randomization. Like it's not like the classical.
No, there's no de-randomization. I just want to say for in classical polynomial time classical algorithms, whether you're using log n pure bits of randomness or n bits of randomness, you can't tell apart. So, and here,
It's very simple.
and this is whether the input is being prepared from n bits of entanglement or log n bits of entanglement, quantum algorithms are incapable. In that sense,
Yeah, in that sense, yeah.
not a de-randomization sense.
Yeah, that's a really nice perspective, and that will be my next slide basically. Like the one motivation, one way to think about this high or low entanglement business is that it's like some sort of an analog of randomization or like de-randomization in some weakness, but very native to a quantum property that has no mapping to like things that are not quantum.
Good.
More questions? So yeah, like I said, like in some sense, the motivation comes from like classical CS, where de-randomization plays a pretty large part, like in many places. I don't need to like summarize it here because you guys know it already. Pseudo-entanglement, in some sense, what we are hoping to, like the message we are hoping to capture is that this is something similar at a very high level, crude level. But pseudo-entanglement is like talking about a property that's very inherent, very native to quantum states. No classical. And so what we hope, what we want is that pseudo-entanglement will have applications in domains that are very native to quantum, like quantum gravity, like property testing, like these things. So this is the end of, let's say, the motivation part. Now we will get into some technical weeds and see the first construction with respect to a fixed part. But before that, questions regarding motivation. Okay, then let me start with the technical weeds. Okay, so let's start with states of this form. The F, now the reason I put it, now it becomes clear. F is basically a quantum secure pseudorandom function, and these states are basically phase states. just like a superposition, but F and like that determines the phase of the like each phase is in the superposition. And from these previous papers, they proved that if F is a quantum secure pseudorandom function, that means you can't tell it apart, like given a black box between that, like that from a random function. If that's the case, then this class of states, that's a valid pseudorandom function. Now let's do some relabeling. Yeah.
So now the JLS definition is a very natural quantum analog of the classical notion of pseudorandom.
I think so. Yeah. That's where they got their definition.
That's how they're writing the entire function.
Yeah. That's what. Yeah, that is quite interesting. Yeah.
And when you say these states are pseudorandom, you mean in the computation?
In the computational sense. Yeah, correct. Like the sense, actually, to be a little more subtle, it depends on how you pick that function f. If that function f is like a random function, then this will actually like random like in the statistics.
Oh, okay.
So the guarantees you put on the function, like flows downstream to the guarantees you have on the state.
Right.
Now let's do a equipartition of the qubits and do some relabeling. This is sort of the same state with some fancy relabeling.
So these are the cuts between.
The cuts basically. Okay. Why do I do the relabeling?
Can you just show the last?
Yeah, of course. Yeah.
Okay.
Yeah.
We just partition the input.
Just partition
into
like-
parts.
Yeah, precisely. Okay. Now let's do some more notations. Let's define a pseudorandom matrix, which is basically you take these functional values, collect them to a matrix. Yeah, the same thing, but just like written like fancy this. Why do we do this? The motivation is now the reduced density matrix on one partition or like both partitions. These can be nicely written in terms of this pseudorandom matrix. This is just some math that you take, like some like back of the math. Okay, so we have a clean form of this reduced density matrix. Why do I get? Now, by a simple Jensen, the von Neumann measure of this reduced density matrix, that's upper bounded by log of the rank of the pseudorandom matrix that is. Entanglement in other words now can be bounded by the log of the rank of the pseudorandom.
That seems here. I have lost all any interpreted. The matrix is sort of a truth table representation of the function in this partition in this
Just like the inner product bit. Just can
Yeah. Let me quickly go back.
Yeah. So the rows are indexed by n/2 bits.
Yes, by the
indexed by this.
input
And the ijth place you put whatever function.
Yeah, so that I follow. This row which has been built, what does it mean? And
The row is the density matrix of.
Yeah, this is the density matrix
On the A part. We create
on the A part.
one
Yes, so you
page.
trace out the B part, there's a fixed bipartition. So density matrix.
I'm sorry, is
Yeah,
F
yes.
the thing that is going to distinguish between the?
No, that is the.
No, it is just the function that is like the phase.
That's the assumption.
Yeah. This
F
crypto.
was used to compare.
F is the
The quantum secured with the random.
This is just some notation, like rewriting the same thing is.
So F parameterizes the pseudorandom.
Okay, now we saw Jensen's and log of the rank of this matrix bounds like the von Neumann. Okay, so what is to make these states low entanglement, the most naive thing that you can think of is to make the random matrix low rank. And what is the most naive way to reduce the rank of the matrix? Will you just repeat the rows of the matrix? Like for instance, there's this matrix CF, you take the first row, delete the second and third rows, and just repeat the first row 3 times. That naively reduces the rank of the matrix, right? Very nice strategy. That's what we will do, but in a more fancy way. Why do we need to?
What are you not doing? Because
We will now smash down the rank of this pseudorandom matrix. We will make this CF low rank.
In the problem, you're redefining the function.
Yeah. And why? Yeah, and the reason to like redefine the function carefully, like take some care in those steps, is blindly reducing the rank of the matrix with respect to some silly function that won't suffice, because that might break the security. We need to repeat the rows of the matrix, the pseudorandom matrix, in a much fancier way, much more sophisticated way. Why? Because we need to hide this reduction index. No distinguisher can tell apart this low rank matrix from a high rank matrix. And so how do we make sure that's the case? How do we guarantee that it's the case?
Okay, what does the distinguisher have access to? It has access to the
Copies of this.
copies of row.
Yeah.
So copies of the
No, like the state itself, like copies of the field.
or
Shire.
Shire.
Yeah. Okay, the way to reduce the rank of the matrix would be like with respect to some cryptographically secure function, like 2 to the k1 function that has many collisions. So the ith row of CF will be given by the gith row of this special function G. And how do we define G? It's like a cryptographically secure. We compose two pseudorandom permutations with a modulus here. This makes sure that the function has lots of collisions. So many things in the domain of this function will map to the same thing in the range. It has a lot of collisions. So repeating rows with this function will, like picking rows with this function will mean that you get a lot of repeated rows in this CF prime.
So you have the matrix F.
Yeah.
And then you have this pseudorandom function G.
Yes.
Which itself is possibly prepared using F1, F2.
F1, F2, yes.
So from F and G, how are you coming to F prime?
Yeah, the
So
CF.
the definition was that the ith row of CF is the gith row of.
Yeah. So
I would
I is the
prefer
domain, and so you pick some rows of CF, let's say.
Yeah.
So because the function has a lot of collisions, many rows in CF will map to the same row in CF.
I think maybe the CF prime and CF are switched.
Switched, is that the point? Now the ith row of CF prime is the gith row of CF. Is that what you meant there?
I don't think so, because so G is the function that we are G is the function that we have to repeat the rows. So G has a domain and G has a range.
So many rows of CF prime should be identical.
Yeah, many rows of CF prime should be the same as like a particular row of CF.
So the rows that correspond to G inverse I should be the same as the ith row of CF. So if G of A is equal to I, then the ith row should be equal to the ith row of CF prime should be equal to the ith row of CF.
So how many different rows does CF prime have? Fewer different rows, right?
Yeah, much fewer different.
Keep that line at least for me. For every I, that ith row of CF seems to sit in the gith row of CF prime.
So say there's one row of CF.
Yes.
Say ith row of CF.
Yeah.
And so say I design CF prime. So that row,
copy to G inverse of I.
Yeah, so that row is copied to some location of CF prime.
Many locations.
Yeah, so
either zero or many.
Yeah, many locations depending on how many things you have in the
in the code domain, the inverse.
Yes. So say there are two rows of CF, A and B, let's say. And so A and B both map to the same place C, like with respect to G. So GA will be C and GB will be C. So when I take the 8th row of CF, I'm trying to map that to, let's say, the Cth row of CF prime will now be the 8th row of CF. Same, like by a same sketch, the Bth row of CF prime will also be the. I now see that there might be some fear.
Then it's fine.
Right.
Just 1 second. first of all, the sizes of CF and CF prime.
They are the same. Yeah.
No, so I mean, the way it is written right now, it seems to promise that every row of CF goes and sits somewhere in CF prime. The way it is written, the ith row of CF is in gith row of CF prime, which means then it can only be a permutation, nothing else, right?
Yeah, so I think, I think I made a typo. Yeah. So the message is just that G is the thing that's picking the rows. And when you pick rows by G, then many rows, like a particular row from CF will be copied in many places.
A particular row, ith row of CF gets copied to
like I, J, K.
ith of CF prime is the gith row of CF.
I think that's the simplest specification.
Or you had CF, you throw away some of the rows. You get only a sparser. The remaining things you duplicate, but embed them in some other order.
In some order.
Which
is given by the serial.
Now this whole, the reordering, etc., is mediated through this function.
Present. That is the message. Like sorry for the type.
But then this reordering cannot be completely like crazy. It is also mediated by some pseudorandomness.
Exactly. This is what will come. Precise. Yes.
Got it.
But the pseudorandomness of F and F2 are also defined as quantum.
Quantum security. It can't be in the classical sense. Yes.
But these are classical objects that are quantum secure.
They are classical objects with the quantum secure.
But then you also want the resulting C prime to be the reduced density matrix of some state.
Right. Yeah. And that holds just from the fact that you have this CF prime, and then you can just construct a phase state again. Okay, so let me come to your point now.
CF prime. My understanding is CF prime is the replacement of CF, right?
Yeah, CF.
And then you do CF prime transpose to get your. That question.
Oh, I see. So what?
So CF prime is the new pseudorandom matrix. That's so and
ensure there's the rank is
and that changes the F because the pseudorandom matrix corresponds to some way of picking the function.
Yes. To write the state, we need 2 to the n amplitude. Yes. We now have a matrix which is 2 to the n over 2 by 2 to the n over 2. There are 2 to the n numbers there. We will just treat them as the 2 to the n. That's
okay. So, and just like you said, that was the punchline. So we will prove that CF prime by a series of hybrids, like standards in like these types of like scales, we'll prove that it is CF prime is distinguishable from a random matrix. Then G is distinguishable from a random function. So like a random matrix corresponds to like something that's statistically close to a Haar-random.
But in the assumption there, if that part is distinguishable in a quantum way, and then the conclusion is also in a quantum.
Both are quantum. Yes.
But that shouldn't matter because we're still about classical problem distribution. So the algorithm would be that.
So the conclusion will be violated by some hardness, classical hardness assumption.
No, about a quantum
like quantum sequence, like one-way functions.
Yes, it's like
if that quantum distinguishable quantum, this quantum distinguishable quantum.
So
are you sort of using some classical hardness assumption to translate that into quantum?
No, the hardness conjectures, those are natively quantum.
Oh, I see. They are not
one-way functions that
don't follow from classical.
They don't directly follow from classical.
But therefore classical objects.
Therefore, classical objects, it was boosted to quantum later in like
proofs. There's no implication.
There's no implication. Like
Going from CF to CF prime is a bit.
So you have a CF prime. I won't go into that in detail yet, but the state that corresponds to CF prime can be prepared with like
So that you need G to have some properties.
Then we need to do this G function like in some way, like pick certain types of like PRPs that can like that have this like that have this nice behaviors. Okay, so the techniques are basically collision bonds. Yeah, it's just like, and like at a high level, it's just saying that like you can have a lot of collisions like in a matrix and still and that matrix will still not be distinguishable from a full rank matrix, depending on like how many collisions you have. And there's a wide range of collisions that you can.
What's the definition of collision?
Collision means that, like, let's say 2 rows of this matrix will be the same. So that's like a collision. And now we count the number of collisions. Basically.
So using a series of hybrids, you're just meaning that using what is called a hybrid argument.
Hybrid argument is cryptography.
Now, when you say that one matrix is distinguishable from another matrix, what do you mean by that?
So yeah, what I mean by that, so these are like black box statements. Say I'm given black box that like is promised to be this matrix, or it's the second matrix. And by querying this black box, there's no way to tell apart which one is the And yeah, so like you pick the right parameters for the collision bound to kick in. For example, let's say k equal to log square n, and then it's just false. And so we get a pseudorandom state family with low entanglement that's like log square. And this can be tuned to anything that's strictly more than log. Just by this simple smashing down the rank in a secure way with these functions that has collisions.
So still I'm stuck in the short sentence. So CF prime is distinguishable from a random matrix. Yes.
Yes.
So is this in the quantum query algorithm model?
Yeah.
That is, CF is given as a black box. You can say, give me the ijth entry, and then it will spit out the ijth entry of the matrix, and you can do this querying in superposition like in Grover algorithm.
That's a fantastic question. So I did do this switch at some point. Yeah, like great that you caught it. Yeah. So this distinguishability result, that's indeed in the query mode. The fact that if you are given black boxes that are like one of these two matrices, you cannot or can distinguish. Yes. However, the claim now is this is like a slightly subtle this is like a slightly subtle claim. Is that if you have an indistinguishability result in this query model, then that translates to a similar result for this quantum state model. Why? It's because if you are given these black boxes, one operation out of the many that you can do is to actually prepare these states. Like given a black box, you can actually prepare these states by a single query. And so if you have some like this black box result is stronger than, let's say, the thing that we were like setting out to get.
Just so usually when you have queries in some memory, you stick in a Hadamard here,
Exactly,
here,
yeah.
and the value moves into the face.
Exactly.
So you do the same.
That's the same thing. That's the same. Yes.
One thing which I'm right matching in there. So CF prime was prepared using both the function f and the pseudorandom g.
Yes.
And somehow the indistinguishability of CF prime from random matrix G is only telling something about G. Shouldn't F have some properties for this duration?
The hybrid because that cannot take it.
No, but suppose I had chosen F to be just the all zeros function. Certainly this can't be true.
The hybrid will probably stay.
Yeah, then the hybrid makes up.
Then the hybrid will say one of the three different.
No, I'm just looking at the conclusion over here. CF prime is distinguishable from random matrix for which F?
For those F which have quantum secure.
Yeah.
For those F.
For those, yeah.
Okay,
For
fair.
those if we have this.
Okay.
So it's
So that confusion is only for those F which are themselves to begin with quantum secure.
Yeah.
So, yeah.
If not, then the hybrid, like those like secrets.
Okay, fair enough. Okay.
More questions regarding this?
So I think that basically if CF prime is indistinguishable from a random matrix, then either G is phase or the
Yeah,
that's what I mean.
Yeah, that's what I.
Yeah. Okay, questions regarding here, more questions? If not, now let's formally define pseudoentanglement, motivated by the construction we just saw. It's like two collections of quantum states. And given the keys for these states, each of these states have polynomial sized circuit that can prepare these states. And secondly, one collection has high entanglement and the second has low entanglement, like we just saw it. And thirdly, these ensembles are computationally like not distinguished by polynomial time distributions.
Exactly.
Yeah,
Fn as a large number, Gn as a
F is a, yeah, these will have a gap. Yeah, F and G will have a gap. Yeah. Okay, and here's one more way to interpret our result. We construct pseudo-entangled states with the largest possibility. Why is it largest possible? Because if the low entanglement collection drops down below this, becomes sub-logarithmic, low entanglement, then the same distinguisher that distinguishes like low entanglement states from Haar-random states will distinguish these low entanglement states from a high entanglement collection. The same distinguisher. So this is the maximal possible gap between high and low entanglement. With
you're saying that the gap falls below logn, what happens?
So then there is a distinguisher that can distinguish between that and n. The same JLS factors distinguish. So the gap has to be strictly more than
We have some things which take less than logn states to go, we just go always different, but quantity.
yeah, like strictly less.
No, like
Strictly more than
the lower, the upper bound construction they use polylog, but is it polylog or is it log here?
strictly more than log. It need not be polylog. It's like, yeah,
So
whatever.
although it's not the same flavor, the proofs are different, but they all have the, because you can't have more than, you can't take more than log, pure less than log bits of randomness and expand it out. Therefore, this is, yeah, go ahead.
And these collections is like a bonus feature. This comes because of the way we construct these sets. These are like pseudorandom quantities.
By the way, so just for this one, so suppose instead of polynomial time, this would be more, and reason I was instead of polynomial time, I work with quantum algorithms that take time t. Does that log n get replaced by log t in the whole?
That's a fantastic question. It won't, but not clear from this construction, right? Let me show you a different construction, like in a couple of slides, which will like that will be the reply.
Okay, fair. You have to all the you have to earn your teeth.
Should I? So there are some couple of more slides. Sure. And like the second bonus feature is that, like I said, this is something that like that will not be covered in detail in this talk. See our paper for this, but these ensembles can be prepared with log-term circuits with long range bits. These are like not geometrically longer log-term, but long.
What do you mean non-range?
Like non-nearest neighbor.
Oh, right. But still bounded under qubits. It acts on.
Fannings are all.
So there's also a caveat there. We need one gate with a fan-in that's not bounded. But that's like a super subtle thing. Like we just need this one gate in the end. So it's not exactly bounded fan-ins, but something very close to that.
Is it very different than the one that you're going to that is back on every
so these need not necessarily be query gates, because like when you're preparing this function, like you know the keys, so you don't need to query it. Like you can just like do this function.
So for each key they have the separate.
Yeah, precise. Okay, this is construction 2, and this is much stronger, and this will be the reply to your question regarding like how does this like distinguishability hold for more generalities? And this will also be stronger in the sense that pseudo-entanglement now will be no matter how we cut this. Okay, we proved that the following collections of states are indistinguishable from Haar-random states. Yeah. These are called subset phase states. What's the difference from the construction that we saw before? Now the superposition is with respect to a restricted subset. We still have the phases though. So F, once again, is any quantum secure pseudorandom function. And this mod S, that's the size of the subset.
You mean X belongs to S?
X belongs to S. Yeah. Oh, sorry. X. Yeah, sorry for the time.
No, yeah.
X belongs to S. So the size of the subset is fixed, but the subset itself is chosen pseudorandomly. And by a pseudorandom function. And what we show is that given T copies of this state, say both the subset and the phases are now chosen at random. Then given T copies of this state, the statistical distance between these collections and Haar-random states scale as T squared divided by the size of the subset. Okay. Why are these subset phase states things that we care about? Note that they have, and yeah, so this is how to prove this by representation theory and a bunch of hybrids. But the point is, the entanglement of these subset phase states can be shown to be just log of the size of the subset. So just by tuning the size of the subset, we can make this low or high entanglement. Just by that one parameter, as long as F is appropriately chosen.
Can you go back to the definition?
Of the subset phase state, yes. This is the definition.
I mean, this whole problem, can I think of it as some massive mixed state being generated by choosing S also? So suppose I say, when I go and ask for a particular sample.
Yeah.
Yeah. So you say you will pick an F from some small connection, and then you will pick an S also from some small connection, which will also be somewhat random or super.
Yeah.
And then you will create for me a pure state.
Yes.
But if I step back and look at kind of put a wrapper around everything you are doing, then you are generating a mixed state.
Of course, yeah, definitely. So the proof that these are statistically close to Haar-random states, the proof goes to representation theory, and that is precisely what we do with representation theory. We show that Haar-random states are basically like symmetric projectors, like all of the symmetric subspace. And these states, these are not exactly that. These are like truncated projectors on some like chunk of the symmetric subspace, but still a large enough. So that preserves the statistical distance. And to reply to your previous question, now the guarantee is much stronger in some sense. In what sense? Now we have pseudo-entangled states. Say we forget about the fact that we can prepare these states in polynomial. Say we take both the function, like both the function that chooses the subset and the phases to be like truly random function. So now we have pseudo-entanglement, no matter where the cut is, such that the statistical distance between these collections and the truly random quantum state, like the Haar-random state, scales as this. So T squared divided by 1. This is the distinguishing. Did that make sense? And now by choosing the F and the S pseudo-randomly, we can also have polynomial size circuit distributions.
So that is true for
anything. Yeah. And now by choosing this thing pseudo-randomly, we have like one more hybrid saying that now we get the computational guarantee.
So this business of like going to any cut, like this is secure against any cut.
Any cut.
So do these sets S have to have some expansion property? They shouldn't be confined to some side, right?
Yeah, the size is fixed. The size determines the set is Yeah, this I'm not sure of, but that's a good question. Let me think about
Kind of graph later you have, because otherwise how we cut.
This seems like from like a high level perspective, at least now, this just seems a very vanilla property. The fact that the reason these things have low entanglement is just because in some sense the superposition is just with respect to sufficiently fewer things. Yeah. The lower bound, this gives like a bound, but the lower bound is slightly non-trivial, but we won't go to that, but that can be proven as well. Like you can prove that these are tightly log of something.
So psi f for me was sort of in the previous case.
Yeah.
Psi f was representing the function here.
Yeah.
Into the function just went into the face.
Yeah.
And so every psi f sort of represented that because f of x was plus minus 1 and stuff. Somehow here, this seems like you're restricting the domain of the function.
Yeah.
But on the other places of it, so I
Let me-
what is the corresponding?
Yeah,
is there a classical I need to
Sure. So let me
But also the G is gone, right?
there's no need to pick
The
it.
sparsity of this S is ensuring the.
Yeah, exactly. There's no need to pick it in like silly G. Yeah. And let me say sorry for bad notation again. This should be psi f of s, like psi f comma s. There will be two parameters. Yeah. This is bad notation for my own. Yeah, the paper has this correct. More questions? Okay. Yeah, like I said, the proof is some representation theory thrown in, and then some figures to go to the computation. There's no need to pick any complicated things. There's no need to do anything. Just pick the subset appropriately, and that gives you the low intent.
So the subset is playing the role of G.
Playing more than exactly. Yes.
So is it statistical indistinguishability as stronger property than computational indistinguishability?
Oh, of course, yes. But the thing that we lose is polynomial and preparability. Because the statistical guarantee that comes when you pick random functions. Those don't have polynomial size distributions. So you gain something but lose something.
This trace distance thing is what is it for random?
For
For random
For
trace distance.
randomly chosen subset and like I said, the von Neumann measure is just log of the size of the subset. And just to tune it, just tune the size of the subset. That works. And construction 1 can be tuned as well. I didn't show this, but it can be tuned by something much more complicated than this thing that is just. But that has been limitations.
How do you pick the pseudorandom subset? This is it's a subset, yes, the pseudorandom in a quantum sense again.
Yeah. The way you pick it, we detail the steps in the paper. Like you take a quantum secure pseudorandom permutation and then apply Hadamard's to 1/2 of your qubits, and then do some and then just permute that in a special way. And then And then and quantum secure PRPs have this nice property that if the PRP has a polynomial size circuit, like a polynomial size circuit description, then PRP flipping the PRP, the process of flipping the permutation, that's polynomial time as well. And we do that to throw away the garbage qubits.
Flipping anything inverted.
But this is
Invert.
all the steps. These are all quantum separate. All the steps are similar to how we prepare pseudorandom sets from pseudorandom functions or pseudorandom computations in the classical sense. No,
but the one
this is the Michalitian.
But this classical one will not be reversible.
Yeah. You will have to go through all those.
To ensure reversibility, we have some mode registers.
Then you could do it from pseudorandom functions, but you need to make it from computations and whole bunch of. Yeah.
So is the classical thing that what I was thinking you permute it in a sort, take a first.
No, I don't know. So there's some paper by Michali and Killian who showed how to construct pseudorandom sets from pseudorandom permutations of functions. I don't recall that, but yeah, there's Michali Killian.
Yeah, I know. So if Yeah, at some point people can have tea and you can continue, and if there is only a short amount left, you can.
There's like, there's like 5 to 10 minutes.
People should feel free to go and take your tea.
Yeah.
The speaker should also be right. I want others to get.
Yeah, so this completes phase 2, and now let's say some places where we can have pseudo like this concept to prove some new things. Pseudoentanglement. So high level, like the high level point is pseudoentanglement tells you that low entanglement can't be distinguishable from high entanglement. So any procedure, any place where there's a chance of computing how much low or high entanglement your state collection has, that process should not be polynomial. And where are some applications, like places where this type of a thing crops? Well, one application is in property testing, like for quantum properties. Like for instance, testing the Schmidt rank of a quantum state. Or let's say doing a spectral decomposition and then computing the largest component. These things will, like computing these things lets you compute if the state has high number. And that shouldn't be polynomial. So these property testers fail to be like, these property testers fail to be like too fast.
What do you mean cannot be done efficiently? So what does?
That means that if these tasks are doable, then the procedure that does this task can be leveraged to distinguish between our high and low entanglement. And that's like a contradiction.
Okay.
Break one of the crypto.
Yeah, it will break the crypto.
If
you have crypto and you
can do this.
with simple, so this is like marrying that crypto conjecture with this more quantum things, like things like this.
Something happens. I think you can you share this?
Yes. Okay, and then some more things can be said. For example, there are these distillation protocols that people really care about in physics. And the setting is something like this. I give you a quantum state, like you don't know what the state is, but you need to give me some bell pairs from this state. And the point is, if you can distill bell pairs, the number of bell pairs that you can distill is bounded by the fact that you have low or high entanglement. Like the von Neumann method bounds the number of distillable bell pairs. But can you can the yield of these protocols, which is giving you bell pairs, can this be too high? It cannot, because then just by computing bell pairs, you can find a distribution. Like the low entanglement collection will give you much fewer bell pairs than the high entanglement collection. That shouldn't be possible.
The classical analog that there is some kind of structure that is like seedless.
Yeah, that's what takes my mind.
I see. What is the classical?
No, I think that is it that something like so classical analog of this distillation seems to be like extractor.
Extractor. I see. Yeah. I think so. Yes.
And this would be seen as a certain like seedless cannot exist like a very trivial. Seedless extractor cannot exist like a very trivial thing. But what I mean. I don't know.
Yeah, the high level mapping seems very similar. Yes, the fact that you can squeeze out bell pairs seems like you can't
So
squeeze out
some randomness as the extractor has to be randomized.
I see.
It needs some small amount of pure randomness. Which will use it is.
Either that or it should have two independent.
Yeah, two independent. Yeah. But can you have as many as you want? So that's
So here, when you extract these EPR pairs, these are local operations on the two sides.
No, this can be anything, like quite generic. This is pretty strong. This is saying any polynomial time distiller, no matter how it performs, the procedure of distillation should not be polynomial.
But there was some restriction. I mean, I have a procedure, quantum circuit, which just ignores the input and produces a certain number of EPR pairs. How do I know that I produced it from the state?
So you have like like a quantum circuit that just throws away the input and produces.
Yeah, it just multiplies a few other words and says that here take these registers and they are in EDR.
But how will you get, let's say, more like for this circuit to like succeed? Like, don't you need like fresh qubits set to the 0 state?
That's right. So it will start with some ancillary state.
Oh,
yeah.
So that you don't have here. Like the set, like the
registers. I
the
don't know how
memory.
many ancillary
Yeah,
registers.
no ancillary. The memory is just the quantum. The memory is just quantum.
Thing from not having any further ancillary states.
Sorry, I have a sort of stupid
Sure.
That's the analogous problem. Not having a random, not having a random, extra random.
are low entanglement states, but they feel like they are high entanglements, highly entangled.
Yeah.
This statement is sort of that.
Yes, the glass is half. Think of this as high entanglement, masquerading as low entanglement,
Right.
or like
I would have thought it's low entanglement masquerading as high.
this is basically the glasses this is just perspective in some sense. Like, this is like the glass is half. Depending on how you look, like there could be two different ways.
So you're saying this particular way of thinking about it doesn't make it precise that these are actually low entanglement states.
Exactly.
But is there something that you can, is there some way of thinking about these states where it becomes clear that these are low entanglement states? It's something you can compute some measure of entanglement which gives you a very high number.
So that's a great question. At least I don't know of it. But maybe like that could be something that you can think of, because
Thank you.
Because like the things that I'll show in like the next slides, these are like very preliminary stuff that, and we are like barely scratching this, like barely starting to like scratch the surface like this. Okay, now let me very quickly in a couple of minutes talk about quantum gravity at a very high energy level. Okay, so there are two worlds like quantum gravity theory, and the gravity theorists believe that there's a mapping between these two worlds. ADS and CFT are the two worlds, and what gravity theory believes is that if a quantum state has high or low entanglement in the CFT, then that corresponds to certain different kinds of geometries in this dual world, like black hole lengths or stuff like that. So what our results say is that in the CFT, these CFT states, the fact that these have high or low entanglement, that cannot be distinguished. However, what gravity theorists believe is that when you actually map these states back to the dual world and consider their duals, then those dual geometries can actually be measured. So this gives rise to a contradiction, right? Because one distinguisher would just be you have a state that you don't know has high or low entanglement. You just apply this dual operation, this mapping back to this world, and then just measure the geometries that you have there. And that distinguishes between the states.
Is it mapping a computational thing, or is it just something in our minds?
It's a computational thing.
The hardness is the
exactly. Yeah, that's the conclusion.
No, but
That's
the is also not, we don't get to know the.
So the conclusion is precisely that is the constant. The diction, the mapping actually, then that has to be hard. And that's what this says about quantum gravity.
Oh, there's evidence of saying bad news for physicists, right?
Yeah, in some bad or
It's hard to obtain.
Yeah.
So basically it's saying that with your knowledge of quantum mechanics, there's no way to sort of.
No, I mean, or the other way, if physicists achieve this, they are smarter than quantum.
What specifies that line, the geometry in the area to be easy to measure?
So
It's this Liu formula we discussed last time, right? Which says that the entanglement entropy has a very simple geometric description. You just compute the area of some surface in the world geometry. So I just have the all a computationally efficient process. I assume that that's what's being said, right?
that is
the area of so this kind of thing. Because the dimension is bounded, in some four-dimensional.
The only hard thing can be the math.
The only hard thing can be. Yeah, precisely. Okay, let me quickly talk about one more application that we have. This is very native to the multi-cut thing, like the subset phase test. This is in testing matrix products. These are special type of states which have a parameter called the bond dimension that determines if the state has high or low entanglement. And these are pretty widely applied in tensor network type simulations of quantum states. The question it poses here is, say I am given many copies of a matrix product state. Can I say that the bond dimension, this parameter that I talked about, is a K, like bounded by K? And previous lower bounds had no dependence like on this parameter, this bond dimension, and were loose, like in the regimes of like high bond dimension. What we show is that pseudo-entanglement implies that any tester that's trying to test if a matrix product state has high or low bond dimension should not be polynomial. The number of copies should scale as random. If K is like super polynomial, then the number of copies will be lower, become super polynomial. Why? The reason is, if you can do this, all these subset phase states that we saw, since they have low or high entanglement, no matter how you cut this state, this property implies that they have a valid matrix product state description. So if you can actually compute the bond dimension of a matrix product state too well, that implies that this whole thing can be leveraged to distinguish between subset phase states of high or low entanglement. That shouldn't be possible. And like a Haar-random state will have high bond dimension, no matter how you cut it. Okay, future directions. Can we prepare pseudo-entanglement with near-term quantum computers? When I was talking about preparability, I said that we still need some long-range gates, like in the preparation procedure. But can you remove that? Can you still get pseudo-entanglement with whatever hardware Google has? There are conjectures that that's probably true. Like you can get pseudo-entanglement and pseudorandom states from restricted to nearest neighbor quantum size. But there's no proof of that yet. Proving that will be really nice. Yeah, like I said, and for these types of hardwares that we saw on Monday, the ones that Google have, just tuning the depth seems to suggest that the states can have high or low entanglement. Like tunability just comes from the depth, like tuning the depth of the circuits. Like there are conjectures that all of this is true. There are simulations that these things are true, but there's no justification yet mathematically. And like I said, the reason that I stand here today is to tell you about pseudo-entanglement and tell you that we have only barely skimmed the surface, barely skimmed the surface. So we want you to think about applications of pseudo-entanglement, like say motivated by things you have in theory CS, which can be ported to quantum. And like I said, the motivation for pseudo-entanglement, a lot of these connections, there are lots of connections to things you have in theory CS, and the motivation is just designing some sort of a natively quantum version of randomness. And that's what I like, and that's hopefully the things that this talk has motivated. And let me end with a few more pointers and let us know of more applications of pseudo-entanglement. Yeah, let me end with a few more pointers. High or low entanglement is just one of the resources that makes a state quantum. But there are many other resources like stabilizer, rank stabilizer, fidelity, many other resources that are very natively quantum. So can we, these are collectively called magic. So can we generalize pseudo-entanglement to these resources? And the answer is yes. We recently had a paper where we considered pseudo-magic states and showed many other applications of pseudo-magic in areas native to quantum physics, like chaos theory and many other places, like more property testing results. So pseudo magic is a thing. And check out our new paper. And yeah, pseudo magic is the same as pseudoentanglement.
So a stabilizer rank
Yes.
is the same as this, basically this quadratic character, right? I mean, you want to express. So, this is true. I mean,
So I think the stabilizer rank, like these magic measures collectively, what they're trying to measure is how close or far you are in a particular distance metric from the state of Clifford states. So
is there a simple definition of stabilizer rank?
stabilizer rank, the simple definition is, say you have a quantum state, like a generic one, and I want to write it as a superposition of many stabilizer states. The number of stabilizer states that we need at minimum is the stabilizer.
What's the stabilizer?
That's like a state that's preferable by Clifford's.
Oh,
So it's somewhat similar to the Schmidt-Randolph state, but in the stabilizer, the basis is like the set of stabilizers.
We have special gates, Clifford gates.
Yeah, Clifford gates is special case, and the reason people make this distinction is that we believe that Clifford, like it can prove that Clifford circuits are classically similar. So the reason quantum computers are powerful has to be something beyond Clifford gates, and that's what this is trying to do. Magic is this like non-Clifford resource, and all these measures are trying to measure how much non-Cliffordness you have in this.
and there are no ways to lower bound the stabilizer rank, right?
Yeah,
Those are very hard.
That's are very hard. And for our pseudo magic states as well, we don't work with stabilizers. These features like stabilizer fidelity, they are much simpler. It's still not known if you can design pseudo magic states with stabilizer ranks. That's a great point. Yeah.
Is magic in some sense a measure of the complexity, the circuit complexity that you need to prepare a state?
You can think of it that way, but I think that's a little dicey.
Okay.
Magic in some sense is measuring the number of non-Clifford resources.
Right.
But for instance, one measure of magic could just be the number of t-gates, and t-gate is a non-Clifford. But there would be many other more sophisticated measures of magic. And every physicist has their favorite magic measure that for a particular thing they care about. And there are thousands of definitions.
Okay.
It's very hard to coherently squeeze them into the same. But it depends on the thing that you get. Because these are all distance metrics from a particular class. And depending on the distance metric, the definitions. So we have pseudo magic states. The highlight is applications to quantum chaos. This is like a natively quantum application again. And finally, so can we have a more like a generic pseudo resource theory of quantum? That's what this is building towards in some sense. And finally, can we relate pseudoentanglement with Hamiltonian complexity? In the sense that there's an upcoming paper that we have which does this. In what sense? So far we only talked about quantum states like pseudoentanglement with respect to given many copies of a quantum state if they're distinguishable or not. But say slightly change the setting. Say now the input is the description of two Hamiltonians. And I want to know if their ground states have low or high entanglement. And physicists have a name for this, volume law versus area law. And the thing that we show is that this is hard to distinguish. Given description of Hamiltonians, no polynomial time procedure can tell apart if their ground states have volume law or not. And one technical novelty here, if you have been following the definitions, is that for the pseudoentanglement constructions that we saw, the security was hinged upon the fact that we didn't know the circuit descriptions that prepared these states. Whenever we had the circuit description and not just polynomially many copies of the states themselves, these functions, like these states, failed to remain secure. But that's not true for this new construction that we will post in a few weeks. these are secured even when you are given description of the circuits that we practiced. With pseudo-entanglement across multiple cards, in some sense in the strongest possible sense, with maximal.
Given the circuit, we won't invert the circuit.
You don't, yeah. So given the circuit, there's say I give you two circuits. One is promised to have states of high entanglement, and the second is promised to have states of low entanglement. And that problem setting is telling you like tell me which one is that. So flipping the circuit doesn't immediately help.
No, I'm just being silly. So presumably one circuit starts from the all zero state and somehow produces the
right. Yeah. So both circuits start from the same reference state.
Same reference state.
Yeah.
But if you took the first circuit and ran the inverse of the other circuit,
right.
It should not lead to zero, right?
It should not lead to zero.
So wouldn't that?
We show that that's not possible. If that were possible for the circuit families we construct, then once again some crypto conjecture will be found. And that crypto conjecture has been proven to be like quantum security. And that's the end of it. Thank you so much for listening, and thanks for being like slightly more than that.
So, forget the theory of pseudoentanglement over there. Doesn't say the following, that is under certain cryptographic arrangements, believable or not believable.
Yeah.
That if you are just an efficient quantum observer observing nature, God really doesn't have to throw too many times.
Yeah. That's the great message. That will be my sales pitch for the next.
Logn entanglement is efficient.
Yeah. So, thinking about this, I'm wondering whether you can think of all these computational applications negative monomials on some products of
yeah, I think so good. I'm not like I think what you're saying is something that we think of, let's say, these functions that as some degree t polynomial of certain degree. And say I don't pick them pseudo-random, but I pick some random degree t polynomial, make this function, to like make this construction. And then yeah, that's very plausible. I think some like so I thought about this very briefly at some point. Sounded possible. I didn't have the math for it, but that sounds very plausible.
So I think you have this fancy vector from pseudorandom.
Yeah.
It can be standard for many times. And then you're saying that what we get random vector and CPL.
Yeah.
So
Yeah.
maybe
Yeah.
we should have.
Oh, yeah.
Very nice talk again.
Thank you. Thank you.
You are around so today is time for you are around tomorrow.
Yeah.
I'll catch you sometime in the morning tomorrow.
Yes.
So we are supposed to meet in the afternoon.
Yes, absolutely.
So around maybe
2000. Yeah. Where are you around?
In my office.
Oh,
Yeah. You are here.
Yeah.
No, I'm saying
For lunch.
for lunch you know where to.
The canteen is somewhere.
Yeah. Unfortunately, I have something planned at
Yeah,
home, so I won't give the lunch with it.
Sure.
But after lunch,
Sounds.
Yeah.
So I'm free now until 50.
Yeah.
So the representation theory side, I was wondering, because there's a stuff of golden gates and so on by Sarnath and people like that. No, like you take a bunch of small gates and you want to construct a equidistributed vector point, let's say some D group, maybe SU2, for example. So there are these things which have spectral gap of the spectral gap of certain operators comes in. They want to make it optimal. So it's like a Markov chain on the three groups. They are not going to. I mean, they have only. They're like bounded number of outgoing things, the vectors from each. So you don't get anything that is uniformly, what's the word? That is bounded additive liquid derivative with respect to the base measure. But you get these point masses which become very nice. So is that related to the statistical side?
The proofs that we had, they were like much more tangible. Those were just like standard representation, like very basic representation. Just like rewriting the phase state in terms of like a projector and one distribution. Like something about and that suffices.
I see.
So we don't need too fancy. But maybe for this more complicated construction, maybe we need something a little more fancy.
I see. And so somehow these low degree polynomials that you would be so you're taking like some I guess some pp to the n and you're tensoring it n times or some t times.
Yeah.
And you have some low degree polynomial p and it will have some. It's a complex. It is a complex number, and you have the tensor distribution.
Yeah.
So even if it doesn't concentrate, that is good enough. You still would need to say something about this. You have the other measure. This is the uniform measure, Haar measure, and then you also have this new tensor. This is pseudorandom measure, new tensor t times. And you take this polynomial. So this you would if these two can be distinguished, that breaks through. But if this does not concentrate, if it concentrates, then what it means that this should not concentrate. This should concentrate something close by.
Right.
But if this does not concentrate, then you would mean that does there also have some conclusion if it doesn't concentrate?
And this measure is like. Yeah, I don't fully follow this.
So maybe I should write R here.
Yeah.
No, I'm saying that. So suppose that. So isn't it the case that these circuits they measure something, right? So they take some observations and then they use that to distinguish.
Right. Yeah. They take some measurements.
So are these circuits of Haar to the T gamma? Gamma mu to the tensor T, or are they just circuits of are these distinguishing circuits of this separately of this and then they take some observations and then they take statistics of those observations?
Oh, like separately. So the
Separately.
the distinguishing is promised that the state comes like is like can be like so like the state is like one of the two cases. The first case is like T copies of all T copies.
Okay.
But not two of them simultaneously.
And then you just have one such thing. You don't have multiple.
No, yeah, just one drop.
Okay.
Then fix the state.
Okay. So then if this thing doesn't concentrate, it's probably useless, right?
Yeah.
It has to concentrate, and then if this also constitutes the same thing, then something can be got out of it. You can say it cannot distinguish.
What our new constructions show, the things that we haven't posted, is that say you're given two cycles. Like say these are like two different cycles. One has high entanglement, second has low entanglement. Then even when you are given the description of both the cycles, like you can't tell apart which one is which. For that, the distinguishers could potentially prepare both types of states and still free. Like do some joint measurements like both. Like
so here mu is circuit for mu is not.
Yeah, so like for both is for this new instance. The one
which are the two mu and
like mu1 and mu2. Now,
okay.
Now this will no longer be Haar-random.
Okay.
Now this will have nothing to do with Haar-random. What was one high entanglement connection and the second one?
I see.